Hello and welcome to Rapid C++ Development, combining Embarcadero C++ Builder with Microsoft Visual C++. Your instructor is Rob Swindell, Embarcadero MVP.
So far, we've shared integers and strings, single byte character strings, between the DLL and the application and back and forth. You probably will come across a case where you'll want to share more complex data types like structures or unions. I'll dive into that now. You want to, of course, define the structure in the header file that's shared between the application and the DLL. So I'm going to go ahead and use the Visual Studio created DLL header file here to define the structure that we're going to be using. So I'll just call it struct test. The contents of the structure are actually important, and also the order of the elements is potentially important. The types you use and the interpretation of those types. So if you're using like a macro like Word, that's kind of a Windows macro for 16-bit integers, then you want to make sure that's interpreted as a 16-bit integer, both in the application's compiler and in the DLL build environment. If you use a data type perhaps a little less specific, like int, then that could be sensitive to different environments, particularly mixed 32-bit and 64-bit environments, where an integer could be either 32 or 64-bit. So my recommendation would be to use the types for integers from the standard int header file. This is part of C99. And this gives you types with specific bit widths for integers. So you could say like int32_t. It specifies that you mean a 32-bit integer, and that should be universally accepted as such. No compiler, tool chain, and architecture should interpret that as something else. If you want, say, at least 32 bits, I think there's a at least 32-bit int, least 32. There's also a int fast32, which tells you I want the fastest integer representation that's at least 32 bits. So it's, that's probably not a good one because that could be interpreted differently by different compilers. So you want to probably stick with the specific types. This is a signed 32-bit integer. You would use uint32_t if you want an unsigned 32-bit integer. In this case, I'm just going to go ahead and stick with signed types, just for examples. I'll call this .word, and then we'll have like a uint8_t. Let's have it like an array. An odd size is good. So this is probably a good example of a simple structure. The padding between, if there is any, the alignment and the required padding between elements in a structure is implementation dependent. So the C standard does not dictate whether or not there is actually space between these elements in the memory and how much space that would be. So kind of the normal default padding would be that you'd want natural alignment. So a 16-bit integer would fall on a memory address that is evenly divisible by 2, whereas a 32-bit integer would be stored in a memory address that's evenly divisible by 4. In this case, if the structure starts, say, at offset 0, so this member would start at offset 4, and then since 4 is evenly divisible by 2, there's no padding required here. This last element, being an array of bytes, only needs to fall on a byte boundary, which is really every address, so that would be fine. The default structure packing can be overridden with command line options to the compiler and also with preprocessor directives. I'll demonstrate those later. For now, we'll just stick with the default packing and see what the difference, if there is any, between Visual Studio and C Builder with regards to their interpretation of the structure definition. So in order to pass this in, we'll pass it by pointer. And then it's a good idea to pass the size of the structure. That's going to allow us to double check that both environments agree on the size of the structure. This is the function definition. And we'll do some checking here. Let's go ahead and make this function return an integer. Give us an idea of success or failure. Kind of the normal C standard is an integer. A function that returns an integer with an error status 0 indicates no error or success. So I'll go ahead and say if size does not equal size of star test, and we're going to return a non-zero error. Gives us an idea that something bad happened here. Otherwise, we'll probably, well, this is probably fine for now. We'll just do a size test. We could also modify the structure. So let's say if you call this function, we will set all the bytes in the structure to 1. So we'll check to make sure that the size matches Visual C interpretation of that structure, and then we'll set every byte within that structure, the pointer that is pointing to the value 1. Oh, and I need to redefine that as returning integer in the header file so they match. And that's why you always want to include your public header file in your C file, just to confirm your function prototypes match. And return 0 on success. I can't write it because the application's still running. Windows, you can't overwrite DLLs that are executing. Okay, so let me run my implib again. And then let's see, now we want, when we click this button, struct test. So in this case, we don't want to use a pointer here because we're actually instantiating the test object. One shortcut for initializing everything to 0 is that. And then we'll go ahead and call that test function. It's in the C namespace, so : test. And let's capture the result. And then we can put the result in the edit box. Control F9 to compile. I forgot the size argument. So being C++, even though this is an integer and this is a string, it's going to do the magic to convert that integer to a string using decimal representation. So let's run this. Hit test. Oh, look. It says 0. So that's telling us that our test function returns 0, success. We're trusting that the test was actually modified. This test structure was modified. So let's go ahead and put a breakpoint here and click that button again. And then, so if we look at test, so here, you see here, it is successfully set to all zeros. If you didn't initialize it with this, of course you'd have uninitialized values, possibly like hex CD or some other garbage, some pattern if it's a debug build, but 0 is what we want for our test case here. And we call this function, it should set it all to 1. So I'm going to say step over. And then, oh, there we go. We see now all the fields were set to 1. And apparently they both agree about the contents, or the size, excuse me, of this structure, how many bytes that should be. If we're not sure, we're curious, we could output that to debug output, or we could put the content, the size, into that edit box. So we could even do it in the constructor up here. So the default value of that will be the size of struct test. Let's give us a quick way to check what the actual size of that structure is. Okay, so 12 bytes is what C++ Builder is saying that structure size is. We know now that the Visual C agrees with that interpretation. So 4 plus 2 is 6 plus 5 is 11. So there is some padding in here. Being that this is 12 bytes, that indicates that this value is at offset 0. This value is at offset 4. This should be offset 6. But since it's an odd number, it went ahead and included an extra byte of padding at the end. Because 6 plus 5 is only 11, and it's a 12-byte array. So what I'm suspecting is if we change this to a 6, and we rerun our code, we don't even need to rebuild the DLL, but we do want to rerun our code. So it's still 12. So the padding in this case is at the end of the structure because it was an odd number of bytes. It adds an extra byte at the end because anything that follows that memory will want to be on an even byte boundary. As another test, let's try just to demonstrate how padding works. We'll put that back to 5. We'll put another integer down here, unsigned int, call it u, rebuild. Oh, I don't think it relinked. Yeah. So it doesn't know. Yeah, we need to do a make. Okay, so now we're 16 bytes. And that's because an integer is 4 bytes. So now that 0 is in between these two. That 0 that it added at the end is actually between these two. Or I should say the 0, the padding. There's 1 byte of padding here that's being automatically inserted by the compiler. And then this field would be at offset 12. 6 plus 5 is 11, plus 1 byte of padding, 12. And it's a 4-byte integer. Happens to be because 32-bit architecture with a 32-bit integer. So this structure is compatible between the two environments, and that's assured by passing the size. It's not perfect. It's possible that the compiler, like say, one compiler could put padding here, and then another one could put it at the end or between two other fields, and you wouldn't know that just from the size of the structure. It's a good smoke test, but it's not a complete check to make sure that the offset of every element is exactly the same offset between the two compilers. Some elements of structures, like bit fields, are completely implementation dependent. So if you have something like int b:1, you're saying this is 1 bit. How that bit is actually stored, represented in the structure, is definitely implementation dependent, and you may see differences between the compilers again. So tread with care. All of these gotchas or caveats also apply to unions. So whether it's a union or a structure or a union of structures or whatever, you're going to have potential issues with structure packing and padding and alignment. So the Visual C command line compiler, so that's CL, compile and link. If you look at the help, I think you'll see options for controlling the packing and padding. There we go. So the Visual C++ /Z, lowercase p, and then a number tells the compiler to pack on certain byte boundaries. You can also control this in the project settings somewhere for the compiler. You can also override the default structure packing in Visual C++ using the struct member alignment option if you want to make your structure smaller. But if you do so, then you also have to control how the structure is interpreted in C++ Builder so that they both agree. So let's go ahead and try changing this to make this what you call packed structures by default. So there's really going to be no additional padding added. Now, the advantage of that, of course, is your structures are a little bit smaller. So if you have a lot of them in memory, maybe you want to do that, you're storing them on disk, you're sending them over a communication interface like a network interface, then maybe you do want small structures. Doing it globally like that with compiler option is probably not desired. You might have a lot of structures that would require additional code that the compiler is going to have to insert to deal with unaligned values. So you might end up with bigger, slower code, even though your structures are smaller. So you probably would want to do that on a case-by-case basis and not globally with a compiler option like I showed. And you can do that with pragmas, but I'll demonstrate first here doing it globally. We rebuilt that. We don't actually need to rerun implib because we're not changing any symbols. We'll go ahead and make sure this is current. We run it. So C++ Builder says that our structure is 20 bytes. We click the button, which will then execute our DLL function called test. The result is -1. And that's because of that option we changed where we changed the default structure alignment. By specifying 1 byte alignment, every element is going to exist on the next available byte. Every element in that structure is going to be placed in the next available byte. There's going to be no padding between them. So like I said, you end up with inefficient code, although your data is smaller. And C++ Builder is going to use some kind of structure padding by default so that the code is more efficient in dealing with the structures. So now we have the two environments don't agree. The code did not run correctly. So hence we got this -1 failure when we executed the code, the function. To change that, we could do it globally in C++ Builder. Again, not recommended, but I want to demonstrate that. Data alignment, okay. That's interesting, quad word. Okay, so now that we have a clear structure size mismatch issue between the two entities, the application executable and the Visual C++ library DLL. So I'm going to add a function to get the size of the structure. So we're basically querying the DLL saying, what is your idea of the size of the structure? Okay. Now we've added a function, so we're going to have to recreate our import library. And what I'm going to do here is go ahead and create two edit boxes. I can do it with copy paste here. And I'll add a couple labels here. I'll call this BCB, or just CBuilder++. So this is going to be CBuilder's idea of what the size of that structure is. And then another label for the second edit box. Okay. So now we've got edit 1 and edit 2. Back to our code. So edit 1 is definitely going to be that. Edit 2 is going to be get size. And that's running in the constructor. It's maybe not a good idea to do it in the constructor, but we'll go ahead and try that. There we go. So we see the mismatch here. CBuilder gives us a size of 20, And Visual C is saying that the structure is 19 bytes in size. Let's do a little experimentation. See, maybe it's this bit field that's the issue. So I'll take that out and recompile. Oh, are we getting quite, okay, still off by 1 byte. So there are pragmas that you can use to control packing. Microsoft and Embarcadero agree on how to override the structure packing on a case-by-case basis using pragmas. And that syntax is this pragma pack operation. So you call pragma pack push, that takes the current structure packing value, pushes it on a stack. You override it with a number of bytes. So in this case, it's a single byte, meaning no padding. And then after you've defined all your structures in unions with no that you want that overridden packing, then you would do a pack pop to restore the original structure packing value, whatever that was. Previously, I had overridden the global structure packing default. I'm going to change that back to the default. Changing that back to the default, that'll test that the structure packing pragmas are working correctly. And now I should be able to get the same structure value in both cases, in both the DLL and the application. Ta-da! So the pragmas work on overriding the structure size, and both the DLL and CBuilder agree now that that structure should be 15 bytes in size. We run the code, step over, F8, check the value. 0. 0 is success, if you remember. So now the test contains a bunch of 1s rather than the default, which was 0s. Here we go, a bunch of 1s. So that's how you handle structure packing, padding, alignment issues, and compatibility between the two environments.